It's working? Okay. Okay, so yeah, I'm going to talk about operator learning, and so this will be based on a joint work with my collaborators, Diana Alikas, Samoto, and Alex Johnson, who are all based at Cornell. I'm working in the broad area of scientific machine learning, which aims to combine numerical techniques for working with, for discretizing or working with partial differential equations, which have been derived in the past 40 or 50 years, and novel machine learning techniques like deep learning to take into account the amount of data available. And so this field can be roughly divided into 3 sub-areas. So depending on the physical systems you are interested in, or the amount of data available, the type of properties you want to discover. So for instance, if we have a small amount of data regarding our systems, but a lot of prior physics information, so typically we might know the partial differential equations, so the mathematical models that describe our system, then there is this field of PDE solvers, which includes techniques that you have certainly heard of, like physics-informed neural networks. On the other hand, if we have, I would say, some amount of data and some amount of prior physics information regarding the system, we have PDE discovery. So in this case, you might have, for instance, access to, you might have information regarding a dictionary of terms in your partial differential equations, terms like du dx, u squared, x squared, etc. And you might be interested in discovering the coefficients in front of these terms, so the coefficients in this library. And so there have been several techniques that have been proposed recently for doing this, achieving this kind of goal, like SIND, for instance, sparse discovery of dynamical systems, that either rely on sparse regression techniques or symbolic discovery algorithms. And so the great talk that we had before is, I believe, lies in this area. And so the advantage of PDE discovery is that you have a human understandable description of your system, but you do not have a fast PDE solver. You still need to solve the equations if you encounter a new problem. And so I'm interested in the later area called operator learning, where we have lots of data regarding governing our systems, but we don't have prior physics knowledge, or we have very little amount of physics knowledge regarding our system. So in this case, you might have data like source terms and solutions, and you try to discover an operator that maps source terms to your system to the underlying solution. And so the advantage of these techniques is that this will give you a fast solver, even though it would be black box, for solving your system that you can then embed into parameter optimization or design or ways of forecasting techniques. And so all of these techniques are kind of complementary and will tell you different things regarding your system. So PDE discovery gives you a nice understandable form, whereas operator learning gives you a fast solver. And so there are also techniques that lie in between. So this is like it's like a continuum. So in between here, you might have techniques like physics-informed neural operators, which take into account some terms that you already know, and some terms that is unknown and for which you try to find an operator. So if you are interested in the later area, so Alex and I have written a recent survey on operator learning, which has a numerical linear algebra flavor to characterize the existing neural network architectures that have been recently proposed. So what's operator learning? So in this field, our aim in this area is that we have data governing our systems. So we have an underlying unknown partial differential equation, so the form L of u equals f. And we aim to discover the solution operator that map a source terms f to a solution u. And so the idea is that you have your physical systems or your existing legacy code, your existing legacy numerical solvers. You can excite your system by selecting source terms or forcing terms f here, observe or measure the corresponding solution u, and then from this, you collect those data, f pairs fj and uj, and you try to compute an approximation to A here, which is your solution operator mapping source terms to solution. If you have like a time-dependent problems, f might be your initial condition, and u might be your solution at time t plus delta t. And so typically we people choose F to be random source terms, sampled from a Gaussian process, and then acquire solution and train neural networks to approximate this solution operator. So they proposed a novel type of neural network called a neural operator, which is basically an infinite dimensional analog of a neural network in the sense that it takes into input functions and output a function. So it's a kind of an analog of a neural networks in infinite dimensions, and there are some interesting properties on how you might discretize the input and output function spaces. And so the main neural operators algorithms that have been recently proposed are of different types. So I've written 3 here, but there are like hundreds of papers that have been published in the past 5 years. So the first one was proposed by Karniadakis' group at Brown, and is the deep operator network, the DeepONet. Then we have the Fourier neural operator and the deep green approach. And so all of these techniques essentially try to address this problem and differ based on the underlying neural network architectures that they use. So the DeepONet is based on a branch and a truncation network, and you can interpret it if you are from a numerical linear algebra background as trying to perform a low-rank approximation or low-rank decomposition to this solution operator. The Fourier neural operator here is based on the fast Fourier transform and convolutional neural network, and has a nice connections with constant coefficients partial differential equations with periodic boundary conditions. Whereas the deep green approach here is based on an autoencoder. And so all of those techniques are kind of black box, so they are very difficult to understand because they are based on neural network. And so it's especially very challenging to derive theoretical guarantees and to derive theoretical results, and in particular to understand how much data do we need to train those networks. So there have been quite a lot of work on the approximation theory side, so trying to understand the size of the network needed to approximate a given solution operator if it lies in a certain class or if it corresponds to a certain type of PDEs. But there have been little work on trying to understand how much data do we need, and that's the area where I'm going to focus on today. So the state-of-the-art results regarding sample complexity, so characterizing the amount of data needed to train neural operators or needed to approximate given solution operators, only focus on self-adjoint operators, so namely uniformly elliptic partial differential equations. So these are the kind of results here, and these results essentially says that you need justify that you need very little amount of data to compute a good approximation to the solution operator. But they only focus on a restricted class of operators, self-adjoint, was researchers in the field apply these techniques to many complicated partial differential equations like time-dependent, nonlinear, etc. So this essentially gives rise to the fundamental question, can we recover the solution operator when one cannot query its adjoint? So if we are looking at time-dependent problem, we don't have access to the adjoint equation, which would be like, for instance, a backward hit equation. And so we can't collect this data. And so we are trying to understand fundamentally and from a theoretical perspective whether it's possible to recover a good approximation to this solution operator when we don't have adjoint data regarding the operator. And so as a motivational example for this talk, we're going to consider the simplest setting of non-self-adjoint problem. So we're going to consider time-dependent, so parabolic partial differential equations of this form, so du dt minus this term here equals f of xt. So f here is our source term, so we collect data of the form f and corresponding solutions u, corresponding time-dependent solutions u. And so the only result that characterize that gives sample complexity estimates for this class of PDE tells us that if we use this number of training data, so epsilon to the roughly minus d over 2, then we can compute an epsilon approximation to the Green's function, so to the solution operator of these partial differential equations. And so this is this is like a probabilistic bound in the sense that we use random functions f sampled from Gaussian process. So this theorem comes with high probability bounds of high probability guarantee. And so how do we prove this type of result? So we use, so this paper uses two different techniques. So the first one is some numerical linear algebra techniques that I will describe later. So in the sense that we try to approximate this solution operator, which for this class of PDE, we know it's an integral operator against a Green's function G here. And so the aim is, given a black box integral operator, how much pairs of the form F and U do you need to compute an approximation to the Green kernel here, G? And so this is equivalent in the matrix case to understanding how many matrix vector product do you need to approximate to recover a black box matrix. And the second technique is based on a hierarchical structure, which exploits some kind of regularity estimates regarding the solution, some kind of smoothness regarding the solution. And so I'm going to focus on this building block here. So this the numerical linear algebra tool that we use to learn the solution operator. And so if we consider the finite dimensional setting, where we have a matrix A here, where I'm writing down its singular value decomposition. So we assume here that A is black box, so you can only access it through matrix vector product, and that's our analog of the solution operator. So we know from the Eckart-Young theorem that the best rank K approximation is given by the tail of the singular values of A here, so that's epsilon K here. And so a landmark algorithm that has been proposed about 10 years ago by Alco, Martinson, and Trop in numerical linear algebra tells us that if you have a low-rank matrix, a matrix of rank K, you need roughly K matrix vector product to compute a near best rank K approximation. So to get an error that behaves something like epsilon K here. And so the idea in this algorithm is first you draw a random Gaussian matrix X, then you perform K matrix vector product with A to get an approximation of the range of A. And then once you have that, you need to perform another K queries with A transpose. And collecting all those data, you can return a QZ transpose, this term here, which is a near best rank K approximation to A. And so there's strong theoretical and probabilistic guarantees to characterize how this A differs from the one we try to approximate. And so we essentially use this type of algorithm in infinite dimensions, so you can generalize this to approximate, instead of approximating a matrix, to approximate integral operators. And so you can apply it to the PDE learning setting, so to the setting of operator learning to get sample complexity estimates. But one of the issues here is that this randomized SVD uses adjoint information, so it requires you to sample the matrix A transpose. And so if we look carefully into this paper, there's a key assumption here, which says that we assume that we can evaluate the action of the adjoint P star of the parabolic operator, which is defined as the backward heat equation. And so this is really unrealistic in practice, because first we do not have access to this operator. And even if we were to have access, this backward equation would be unstable, and so we wouldn't be able to realistically collect accurate data regarding this adjoint. And so this brings us a natural question, which is a fundamental question in numerical linear algebra. Can we discover a numerical linear algebra algorithm that computes a good rank K approximation without adjoint? And if we had that, then we could apply it to this setting and get good sample complexity estimate without this assumption. And so to do that, we're going to answer it by looking at the low-rank matrix recovery problem, where our aim is to recover an unknown low-rank matrix A just from sketch for matrix vector product y equals AX. And so we want to see whether there exists an algorithm that can do that and that can accurately return a good approximation to my original black box matrix A. And so to characterize that, we are going to assume that A is what we call epsilon near symmetric and low rank. So it's essentially it's epsilon closed from a symmetric matrix in the sense that the angle between the left and right singular subspace differ by, is bounded by epsilon. And so we are going to consider the set omega here, which contains all rank K matrices that satisfies our matrix and that are epsilon near symmetric. And so this set omega characterizes the set of algorithms, the set of answers that can be returned by any admissible low-rank recovery algorithm. So for instance, if you have your original matrix here, A in this set, the randomized SVD algorithm might return you an answer which is there, whereas another famous rank K approximation algorithm, the Nystrom method, might return you another answer here, A. And so what we see is that this diameter of omega determines the maximum recovery of any reasonable reconstruction. In the sense that if I have this matrix A and I just have information where y equals ax, if I find an algorithm, if someone gives me an algorithm that returns me a matrix here A, a good approximation, an approximation here, I can then construct an adversarial example within this set that can be far away up to the diameter of omega, from which I cannot distinguish between the original matrix because I'm using all the information available. So I can't distinguish between two matrices in this set, and so this diameter of this set determines the maximum accuracy of my reconstruction. And so what we are going to do is to provide bounds on this diameter of this set to determine the existence of algorithms that can return a good rank K approximation. And so one of our theorems tells us that the diameter of omega here is lower bounded by square root of epsilon, in the sense that there is no algorithm that can give you better than square root of epsilon accuracy to this original matrix, no matter how many matrix vector products you have. So even if you increase your number of matrix vector products, you can't get something better than square root of epsilon if your matrix as your matrix becomes non-symmetric. And so the lower bound that we have is sharp because we also have a corresponding upper bound here. And so there are some nice, this is the only thing we know about the set omega. So there are some nice further research in numerical linear algebra to understand properties of this set and to apply it to other class or other structures of matrices. And so this result in particular tells us that the adjoint is essential for low-rank matrix recovery, but it doesn't seem to be needed in practice for operator learning. And so I'm going to show you an example where we apply operator learning to a non-self-adjoint problem. So we are going to consider this convection diffusion equation here. And so we apply a neural operator technique to recover the Green's function from data. And I'm going to vary this coefficient C here, so the perturbation from being self-adjoint. And I'm going to record the accuracy as I increase the perturbation magnitude C. So this is a Green's function that we recover. So as C equals 0, so we have the Green's function of the Poisson equation. And as C increases, then the model becomes less and less symmetric. So this is if I plot the perturbation magnitude against the corresponding relative error, we observe that the relative error obtained by our neural operator technique grows as the perturbation magnitude C. And this is something kind of surprising because it hasn't been noticed in the neural operator community in the sense that people apply it to many complicated problems, but there are still some issues even for simple problems, and the accuracy of the reconstruction in particular depend on the fact that the model is non-self-adjoint. And so we observe that the error here increases linearly with the magnitude of the perturbation, and the variance as well of the result, if I run my model several times, also increases as the perturbation magnitude increases. But if I increase my amount of training data when I train my model, all these lines will be shifted below, so we will still be able to refine the accuracy. And so we want to understand this picture, essentially. And so to do that, we're going to propose an adjoint-free approximation algorithm for operator learning. And so this is it's an extremely simple algorithm. So our aim here is that given a compact operator A, so think of it as given the solution operator, we want to compute a rank n approximant to it just from samples, just from evaluation. So the step one of this algorithm is that we choose a prior unbounded self-adjoint operator L with eigenfunctions phi k and eigenvalues lambda k. So this is our prior operator for sampling the compact operator that we try to approximate. So here L is something like the Laplace operator, and that's connected to the choice of source terms that people employ in operator learning. And then the second step of the algorithm is to return the rank K approximation APN, which is given by the projection of A at the eigenfunctions of the prior operator L. And so this is our form for our rank K or rank N approximation. So this is a rank N approximation APN that is returned by our algorithm. And this one doesn't need any adjoint information because we just sample our operator from the right. And so the nice thing is that this adjoint-free algorithm comes with theoretical guarantees that quantifies how much we differ from the original operator. And in particular, we have this result, which bounds the approximation error between A and its approximation by a factor which behaves like the eigenvalues of the prior operator. So this is kind of surprising because the approximation rate that we have doesn't depend on properties of A. And another factor, LA star, which we know is bounded, and that depends on like regularity and smoothness between the prior operator L and the adjoint of the operator that we try to approximate. And so now we're going to see some numerical example of this adjoint-free approximation algorithm. And so we are going to consider a linear elasticity equation, which basically models the small deformations of three-dimensional beams under an external force. So this is the corresponding displacement of the beam if I use gravity as the external force. Yeah. And so if we apply our adjoint-free approximation technique to this, so we use the Laplace equation in 3D, we compute the eigenfunctions, and then we sample our solution, we solve at all the eigenfunctions. We get this blue curve here, which basically models the approximation error between our adjoint-free approximation and the current solution operator as we increase the amount of training of data. And we see that the red curve here is a bound given by our theorem, which behaves like O of n minus 2 over 3. So this is given by the decay rate of the eigenvalues of the Laplace of the Poisson operator in 3D. And so we see that we have a good agreement and a tight agreement between the approximation and our upper bound. And so there's still this constant LA star here that we might be interested in characterizing. So in certain problems, you can compute explicit upper bounds for this constant LA star, but there's still a lot of work to be done depending on the type of problems you are interested in. And so to do that, we are going to consider a simple perturbed elliptic partial differential equations of this form here. And we are going to use the dominant term as the prior unbounded operator L. And in this particular case, you can characterize this constant LA star as the perturbation magnitude grows using some perturbation theory analysis, essentially. And you get a theorem, an approximation error between A and its adjoint-free approximation of this form, where the constant here grows like the norm of the perturbation magnitude. And this is quite interesting because it agrees with this neural operator experiment that I showed earlier, where the relative error grows as we perturb the partial differential equations. And so this statement tends to explain the performance of current neural operator architectures on non-self-adjoint problems as well. And it also tells you some information regarding how you might choose your prior operator to minimize this constant LA star here. And so as a conclusion, so we provided a characterizations of low-rank matrix recovery algorithm, and in particular the fact that there is no low-rank matrix recovery algorithm that doesn't require adjoint matrix information. We did analysis of operator learning for non-self-adjoint operator. And then we provided an adjoint-free operator learning algorithm with strong theoretical guarantees. And with that, I'll conclude and thank you for your attention.